Good morning, ladies and gentlemen. What we're going to do today is we're going to review a little bit of arithmetic with complex numbers. Usually we denote this letter Z. Uh, and here we're first given our complex number. Z is equal to 3 minus 2i. We're asked to graph and evaluate the following expressions for Z. Okay? So we're taking this complex number, 3 minus 2i. Let's go ahead and graph that. Okay, where would we find that? So here's our complex plane. Uh, the first number tells us how far left or right to go, and the second number, we can omit the I for the moment, the time being. The second number is going to tell us how far up or down we go. So, okay, starting at the origin. So the first number, 3, let's go ahead and plot that. 3, that means we're going to go to the right 3 units, and then we're going to go down, right? The minus sign by convention tells us to go down 2 units, so minus 2. So this point here, this represents Z, right? This is equal to 3 minus 2i. Okay. Here we're given, for number 1, we want to plot negative Z, or the opposite of Z, okay? So the opposite of Z, we're going to take the signs given to us as positive 3 and negative 2, and we're going to flip them. We're going to take the opposite. Just like the opposite of positive 3 is negative 3, the opposite of 3 minus 2i is going to be negative 3 plus 2i. Notice how we're just flipping each of these signs, okay? This would be denoted positive, and this is a negative, okay? So the opposite of Z is negative 3 plus 2i. Using our conventions, this is telling us to go left 3 and up 2. Starting from the origin, left 3 and up 2. Okay, this is the opposite of Z. Whoops. Opposite of Z. Okay, now you'll also note that we can be sure that these are opposites because if we rotate this point 180 degrees about the origin, okay, this is rotated about the origin, you're going to arrive at this point, okay? That's part of the definition for opposites. Okay, the next thing we're going to evaluate is Z conjugate, the conjugate of Z. Now if you remember, the conjugate of Z is defined as the reflection of our complex number Z reflected about the x-axis, or the real axis. Okay, so here's our x-axis. If we're going to reflect this point about the x-axis, we're going to take this point and we're going to take it to the opposite side of this axis, all right? Think of this as the mirror image, okay? So here's our line of symmetry, and we're reflecting this point about this line. We're going to arrive at this point right here, okay? We can also define this as not only as the reflection, but also as if we take Z and we just flip the sign of the imaginary part, then we'll get 3 plus 2i, okay? And this is, again, the reflection about the real axis. So we'll call this Z conjugate. And another way of writing this would be Z star, okay? These are the same thing, okay? Next up, we want to go ahead and evaluate what is the complex number Z plus 2. Okay, so note that 2 is a real number. We're going to add the real number to the real part of our complex number. Okay, so this is the same as 3 plus 2 minus 2i. And you'll note that I am combining the real parts here, and we're leaving the imaginary parts alone, okay? Because we combine real parts and imaginary parts with themselves. Okay, so 3 plus 2, that's 5 minus 2i. This is the same as taking Z, okay, Z, and moving it 2 units to the right. Okay, so where's Z? Z is right here. We're going to go ahead and move it 2 units to the right. Okay, so now we're here. This, let's count 1, 2, right? If we move it 2 units to the right, this is plus 2. We are now at this point, and we name this point Z plus 2. Okay? Z plus 2. Likewise, if we subtract 2i, that's the same as taking Z, but because now we're subtracting an imaginary part, we're going to go ahead and by convention, move z 2 units down. Okay, so here's z, move 2 units down. This would be subtracting 2i. Okay, and now we're at the point z minus 2i. Oh man, really? Oh wow. Last but not least, we're going to go ahead and evaluate the magnitude of z, or the distance from z to the origin, okay? And we do that by taking the absolute value of z. Where is z? So z is here. We want to know what is the distance from the origin to z, right? And we can define that as a straight line. So here we have that point there, this point here. So I'll go ahead and call this the magnitude of z, if we're to zoom in, right? The magnitude of z. The magnitude of z is equal to the length of this segment right here, the line that connects the origin to z, okay? Well, what's the length of that? Let's use the Pythagorean theorem. Here we have a right triangle, this length here, 3 and 2. We want to know what's the length of this. Okay, so this is 3 and this is 2. Well, let's use the Pythagorean theorem. We know the magnitude of z is going to equal the square root of the legs squared. Okay, the sum of the legs squared. So the sum of the legs is 3 and 2. 3 squared plus 2 squared. The square root of 3 squared plus 2 squared is the same as the square root of 9 plus 4. And 9 plus 4 add to equal 13. And because 13 is prime, the exact answer would be square root of 13. Okay, it's a prime number. That means there are no positive factors or even perfect squares that multiply to equal 13. So this is the simplified form. If you wanted to evaluate this in your calculator, you could do so, but this is the exact answer. Okay, so magnitude of z is equal to square root of 13.